How to handle tons of large volume transactions. Here are some strategies for handling tons of transactions. Horizontal scaling. Deploy multiple instances of microservices to distribute the load across multiple servers. This can be achieved by using containerization technologies like Docker and orchestrators like Kubernetes to manage and scale the microservices dynamically based on the transaction volume. Load balancing. Implement a load balancer to evenly distribute incoming transaction requests across multiple instances of the microservices. This helps prevent any single microservice instance from being overwhelmed by a high volume of transactions. Caching. Utilize caching mechanisms, such as in-memory caches like Redis, to store frequently accessed data and reduce the load on the back-end systems. Caching can improve response times and handle repetitive queries for transaction-related information. Asynchronous processing. Employ asynchronous processing for non-real-time or resource-intensive tasks. For example, when a transaction is initiated, critical tasks like updating balances can be processed synchronously, while non-critical tasks like sending notes and report in async. Event-driven architecture. Use an event-driven approach to handle transactions. Microservices can publish events related to transactions, and other services can subscribe to these events to perform necessary actions. This asynchronous communication pattern helps decouple services and improves scalability and responsiveness. Database optimization. Optimize database design and performance for handling high transaction volumes. This can include techniques such as sharding, partitioning, indexing, and using in-memory databases or NoSQL databases for high-speed data retrieval and storage. 7. Monitoring and auto-scaling. Implement robust monitoring and logging systems to gather insights into the performance and health of the microservices. This information can be used to trigger auto-scaling mechanisms that dynamically adjust the number of microservice instances based on predefined thresholds or performance metrics. 8. Resilience and fault tolerance. Design microservices with resilience in mind. Use techniques like circuit breakers, retries, and fallback mechanisms to handle failures and maintain system availability. Implementing a distributed tracing system can help identify and debug issues in a microservices environment. 9. Performance optimization. Continuously optimize the performance of individual microservices and their interactions. Profile the code, identify bottlenecks, and make improvements accordingly. Consider employing techniques like request batching, response caching, and optimizing database queries to minimize latency and improve throughput. 10. Testing and benchmarking. Conduct rigorous performance testing and benchmarking to identify system limitations and bottlenecks before deploying to production. Simulate high transaction loads and analyze system behavior under stress to optimize the architecture and ensure it can handle the expected transaction volume. Remember that the specific implementation details may vary based on the technologies, frameworks, and infrastructure you choose to employ. It's essential to regularly monitor, analyze, and fine-tune the system to ensure it can handle tons of transactions effectively and efficiently.